In a previous video, you've seen the creation of these fun little ball bearings, and they actually spin really well for a 3D print. So well, in fact, that I couldn't resist printing a whole bunch of them to have laying around to use at will. The only logical result of making a spinny ball bearing was to make use of it in a fidget spinner like this one, which led me to wonder, how fast can this thing realistically go? It's a good thing I printed a bunch of these things too, because I have no idea what's going to happen. Gut feeling, the 3D print will be okay, but I wonder about the non-printed tiny ball bearings inside of it. These 6mm diameter balls are actually ammo for airsoft guns that has been repurposed into load-carrying powerhouses. The balls have done well so far spinning the Fidget by hand, but the question is, how fast can I push it? In order to get this thing going, there's a few challenges to overcome. One of them being how the heck to hold on to it. My first idea was to simply clamp it to something. This design doesn't lend itself easy to mounting, I'll tell you that. I have this 6-inch bar clamp and a 2x4. Just have to make sure the bar doesn't contact a Fidget so it spins freely. A little bit of clamp pressure and voila, mounted. Now this could work, but it doesn't seem stable to me. As soon as I set it down and let go, it decided to reorient itself. I think I'm going to go with something a little more easy to work around. Popping back into the assembly model, I figured it would be best just to include a mounting feature on the test spinner. For that, I want to hold on to the inner race, so I'll open that part of it up. Just need to find a flat plane to create a sketch on, draw a circle with a 5/16 inch diameter, then cut extrude to create a through hole. Now I feel I can hold it down easier. So let's get this thing into the slicer one last time and lay out the 3D print on the build plate. Running through the slicer settings too real quick just to make sure everything is as expected. And I do want to make one change. I want all parts of this to be solid plastic, so I'm changing to 100% infill. Well, let's see how much time this is going to cost me. A little over 5 hours. Let's go. And 5 hours of my time was only 4 seconds of yours. It feels like that's just how the bulk of the videos around here go too, not just the time lapses. Well, everything seemed to come out pretty good, and let's get them off here and start getting it together. This is a really simple print and assembly job with just 3 parts, but I guess it turns into 11 parts when you count each of the 8 balls that go into it. Oop, we have a runner. Get back in there. And just like everything in life, there's a trick to getting it to work, and without this little piece of cardboard with a hole in it, it's nearly impossible. For more info on why it's necessary, in the original bearing video I explained it a little more in detail. Go check it out. There should be a link in the upper right if I can figure out how to do it. Alright, just gotta get these all piled into one side with the inner race offset to the other side. Then it just pops over and works. How about that? I still have to get the cage in place to separate the balls around evenly. Let's do that now. This is the only tedious part of the whole thing, I swear. Once it pops in place, it still works. That's a really good sign. These things are just too cool. Alright, well, I thought I could use the ones I already had printed and unexpectedly decided to create an extra step for myself, but that step is out of the way now. Now that I have the hole in the middle, mounting just got a whole lot easier in my mind. I'm going to bring out the 2x4 again, place the spinner onto the edge like it was before, and hold it down securely with this 1/4-20 socket head screw. Should work, right? And it's obviously missing a hole, so let's fix that by drilling one that's the same as the root diameter of the threads. Should be deep enough. The nice thing about working with wood is that any screw can become a self-tapper. Just gotta get it started, then apply a little bit of motivation. I think I can live with this. Okay, well, got the mounting challenge solved. Now I have to figure out a decent way to measure how fast it's spinning. And for that, I decided to use this Vernier Bluetooth Photogate. And here's the specs, but they don't do it any justice. This thing is super capable of measuring things at high velocities. Being that it's Bluetooth, it can transmit to just about anything. Anyways, I was able to get my hands on one, and here it is. It has 2 different infrared photogates for measurement on it. as well as an input that can sense an external cat toy laser. On the backside it has a data port if you prefer to be wired, and a micro USB charging port for the internal long life battery. It also came with a rod in the package for a little bit of mounting versatility. Thanks, but I don't know how I'm going to use this for now. And a charging cable to throw in the drawer with the rest of them. Okay, so it has two separate photogates. Why? Well, it's to measure speed. It knows the distance between them and how much time it takes between beam breaks. This third laser gate is kinda independent of the other two, and a nice feature. With a standard dollar store handheld laser, you can just shine it in the hole. Of course, that's assuming your mounting of each piece is aligned perfectly and the laser beam stays pointed at the receiver. This allows you to measure much larger things. Enough messing around, let's get this thing turned on. You can see the lights turning on and off as feedback, showing that there's an object present. And in short, that's kind of all this thing really does. The true power behind this Photogate is in the software that goes along with it, which is available on their webpage. And there's two versions of it, both basically the same thing as far as I'm concerned, but one is free and the other requires a license. Guess which one I downloaded? Yep, the free one. Here's the software, and to get this thing connected I just have to click the sensor data collection, wait until it finds the Photogate, then hit connect. There we go, the red light now changed to a green light. So far so good. It's now sending signals from the gates to the software. So setting up the software can be a bit tricky, but bear with me here. The Photogate is capable of sending lots of different signals to the software. I'm only interested in one of the signals from gate 1. I can turn everything else off. So now you can see that gate 1 is the only one selected. I guess I'm done with this page. Okay, where to go next? Oh yeah, in the bottom left corner I have to change some things as well. By default it's set for linear motion. I want to change this to angular motion. And I'll explain it later, but for now I want the number of spokes to be 1, and the measurement set to revolutions. Done with this screen. Next I need to add a calculated column to the dataset. I hope this all makes sense to you eventually. The name of the calculated column, RPM. Then I want to insert an expression from the pre-programmed set of expressions the free version limits me to. Alright, so parameter A needs to be changed to 60. Then column X needs changed to velocity. Then I just need to pan over and verify that this is raised to the power of 1, because, well, math. Then lastly, I need to make sure this newly calculated column appears on the graph. And then I think that's it. Yep, that's it. Okay, so the reason I typed the number of spokes as 1 earlier is I wanted to test the Photogate settings out and see just how fast it could record everything. Hopefully it can accurately read this thing at high speeds. Later on when I test the fidget spinner, I'll just adjust the number of spokes to 3. Let's get this flywheel onto the motor. Now I kinda tested this earlier and this pulley really whips around. I'm actually going to be impressed with the Photogate if everything works properly. Through the Arduino here I can adjust the motor speed by turning this potentiometer dial. So what do you think? Is the Photogate going to be able to measure this? I guess we're all going to find out right now. I just got to click collect and it's off to the races. Starting off with a slower speed, it's registering a little bit of a minor fluctuation. Let's crank it up a bit. A little over 3,000 RPM. 5,000 RPM. About 6,800 RPM. 8,000 RPM and what looks like a little artifact there. 9,000 RPM and still the artifact. Just holding it here. You know, I never knew what the Arduino kit motor RPM was. It's probably a little bit faster than this with no load and a bare shaft, but this helps. Ramping it down in steps. The data is sending in chunks here at the end and not really a smooth graph formation anymore. Well, that peaked out at 9,235 RPM. Not too shabby. I was guessing this Photogate would be a fraction of that with this setup. Yeah, data. Just scrolling up here a bit. Every time the light beam is broken, it makes an entry, and it also records when it's visible again as another entry. It also records the elapsed time of each occurrence right down to 5 decimal places of a second. What is that, like 10 microseconds? So now I'm just curious, how fast can I spin it by hand first? Let's get back into the settings here. Angular motion, 3 spokes, revolutions. Done. Add a calculated column. name it RPM again, insert expression, 60, velocity, apply. Turn on the calculated RPM. Alright, looks good to me. Time to see what I'm made of. Oh man, what was that, a little over 800 RPM? That was weak. About the same, 800 or 900 again. This graph is kinda neat. It could actually be used to see how much friction each bearing design has by comparing the curves. 1150. Yeah, all these curves look the same. I'd be curious to compare this to a different spinner assembly and see which one is more freewheeling. Okay, probably 1400 is the best I'm gonna get here. Maybe in a different environment I can do better, but I'm trying to hold everything still to get good readings. Looking at the data, it actually turned out to be 1423. Well, I probably could have planned ahead way better than this, but I'm just making stuff up as I go. The Photogate is too short for the mount I have the spinner attached to, and it obviously isn't going to work like this. I need to raise it up about 1.5 inches. Luckily, that's the true thickness of a 2x4. Yeah, that looks just right. Now the spinner passes right through the middle. I just want to add some zip ties to persuade the Photogate to stay in place. Okay, well, that's it. Enough messing around. I think I'm ready to start testing this thing for real. To start off, I have my air tank set to about 100 psi. I honestly have no idea what's going to happen here. I'm just going to blow air on it and hope it spins, I guess. What was that, about 4,000? Let's go again here. Yeah, about the same. I hear my compressor running, which means I'm dropping quite a bit of pressure and it's just going to slow down anyways. So looking back, it looks like it peaked out at about 4,223 RPM. To be honest, I expected more than this, but it is what it is, right? And even after those 2 higher speed runs, it seems to work just fine. Okay, I cranked the pressure up into the red here. What is this, maybe a little over 130 psi or about 9 bar? Well, let's get after it. Wow, probably doubled it. A little over 8,000 RPM maybe. And it does still work. 8,180 RPM is the official recorded speed of that run. I was looking this thing over a little and did see an issue that occurred. The cage looked like it was falling out of place. Yup, suspicion confirmed. You know, I didn't even think about that. I'm running this bearing without any lubricant at all. Just plastic on plastic. Tons of friction on this part particularly. You can kind of see how the tips of the cage that wrap the ball have begun to melt out of place a little. This cage needs to be just right in order to do its job. Not too tight and not too loose. Looks like it just wore itself out. And the Fidget works without the cage just fine, but it needs the cage to distribute the load and space the ball so it doesn't disassemble itself. The rest of the spinner is still intact and ready for spare parts installation. I'd call this one a success, even though it failed. That actually took me by surprise here to have the cage fail. Now that I think about it after witnessing everything, the cage is the only piece that actually has sliding friction and not rolling resistance. We all know that friction leads to heat. The bearing cage simply overheated and deformed. The balls are just rolling only on both the inner and outer races. There's unbelievably low friction between all these pieces. Honestly, it makes perfect sense. Every other part is connected through rolling balls. Maybe to improve the speed capability, I could just print the cage from a higher temperature material such as PETG or ABS. You know, everything we learn makes us better decision makers in the future, so hopefully I can use this knowledge to improve any future bearing designs, or other designs nonetheless.